Hello everyone, welcome back to the deep dive.
Great to be here.
So today we're going to start things a little differently. I want you to think about your kitchen,
Okay, my kitchen. I'm there.
specifically that big humming machine in the corner of your refrigerator.
A very cool place to start, literally.
Exactly. Now, we all sort of know the history, right?
Yeah.
We used to use these gases called CFCs like Freon,
Chlorofluorocarbons, yes.
and then we found out they were bad for the ozone layer, so we switched to things like HFC 134A.
We had to, yes.
But here's my question. Why those specific chemicals? Why not just use, I don't know, water or oxygen?
It's a genuinely good question, and the answer is why today's topic is so important. Most students think chemistry is all about reactions.
Explosions, color changes, all that stuff.
Right, but the answer to your fridge question is not about a chemical reaction, it's about physics. It's about the physical personality of the molecule.
Physical personality.
Yes. Today, we are exploring Unit 6, haloalkanes and haloarenes, and we're going deep into their physical properties.
Okay, I have to be honest. When I was in class 12, this is the section I would skip.
I'm not surprised.
I just wanted to get to the reactions, SN1, SN2. That felt like the real chemistry.
And that's the biggest mistake, because understanding physical properties is actually solving what I call the prediction problem.
The prediction problem. Okay, that sounds way more interesting than memorizing boiling points.
Imagine you're in a lab and you synthesize a new molecule. No one has seen it before.
Okay.
Can you predict if it's going to be a gas that just flies away or a liquid? If you pour it into water, will it mix? Will it sink?
So it's like a superpower. You look at the formula and you just know how it's going to behave.
Precisely. And for everyone listening who's preparing for board exams, this is so critical. They love to ask you to arrange compounds.
Arrange in increasing order of boiling point. I remember those questions.
Exactly. And if you're trying to memorize the numbers for every single compound, you're going to fail. There are just too many.
Work smart, not hard.
Yeah.
So, what is the logic?
We have to go down to the absolute simplest level, the zero level.
Let's do it.
The physical personality of any halocane comes down to just three things.
Okay.
First, its molecular weight. How heavy is it? Second, the polarity of the carbon-halogen bond.
And the third.
And third, the intermolecular forces, basically how much these molecules like to stick to each other.
Weight, polarity, and stickiness. Okay, let's unpack this.
Let's do a visualization.
I want everyone listening to close your eyes. Unless you're driving, of course. Imagine two molecules. On the left, we have plain old ethane.
Just a simple hydrocarbon, non-polar, light.
And on the right, chloroethane. Almost the same, but one hydrogen is replaced by a big chlorine atom.
Now, what's really happening here? That chlorine changes everything. First, it's much heavier than the hydrogen it replaced.
Right.
But more importantly, think of that chlorine atom as a tiny electron vacuum cleaner.
The vacuum cleaner.
Yes. Chlorine is very electronegative. It's greedy. It sucks the shared electrons in that bond towards itself.
Okay, so the electrons are all shifting to the chlorine side of the molecule.
Exactly. And this creates a dipole. The chlorine end becomes a little bit negative, and the carbon end becomes a little bit positive. The molecule is now a tiny magnet.
Ah, okay. I can see that. So ethane is just a neutral blob, but chloroethane is a little magnet with a plus side and a minus side.
Correct. And that changes how they behave completely. With ethane, the molecules are like strangers just passing each other by.
They don't really interact.
Very little. But with chloroethane, you have a whole bunch of tiny magnets. The positive end of one attracts the negative end of another.
So they start to clump together. They stick.
Yes, they stick. We call these dipole interactions. And because they're stuck together, you need more energy, more heat to pull them apart and turn them into a gas.
That makes so much sense. So ethane has no glue, low boiling point. Chloroethane has magnetic glue, so higher boiling point.
That's the core concept right there. So if you need the exam-safe anchor definition, here it is.
Okay, let's hear it.
Physical properties depend on molecular weight, polarity of the CX bond, and intermolecular forces. Generally, boiling points and solubilities increase with halogen size and molecular weight.
Wait a minute. You just said halogen size and molecular weight.
I did.
But we just spent all this time talking about polarity and the magnets. I thought that was the key.
You've just hit on the misunderstanding trigger.
Yeah.
This is where so many students get it wrong.
How so?
Well, they look at the periodic table, they see fluorine is the most electronegative element.
Right. So the carbon-fluorine bond is the strongest magnet, the most polar.
So the student thinks, aha, strongest magnet means stickiest molecule. So fluoroethane must have the highest boiling point.
That logic sounds perfectly reasonable to me, but you're saying it's wrong.
It's wrong, because in this chapter, for boiling points, there is one rule to remember.
And that is
Weight wins over polarity.
weight wins. Really?
Yeah.
Even over the powerful magnet.
Yes. You have to remember, the polarity creates a dipole force, which is okay. But molecular weight, the mass, it creates a different kind of force.
The London dispersion force.
The London dispersion force, or van der Waals force. And as molecules get bigger and heavier, this force becomes huge. It completely overpowers the polarity effect.
Okay, that's a bit abstract. We need an analogy. Help me see why being heavy beats being magnetic.
Of course. Let's go to a concert. This is the concert crowd analogy.
A concert, I like it. Okay, set the scene.
So imagine a huge crowd of people. That crowd is the liquid state. Our job is to disperse the crowd, send them home.
And that's boiling, turning liquid into gas. Got it.
First, the ethane crowd. These are very light, skinny people, feather light. They have no magnets on them.
Easy to disperse. You just nudge them and they scatter.
Mm-hmm.
So a low boiling point.
Exactly. Now, the chloroethane crowd, they are heavier, and they're all wearing those magnetic badges we talked about.
So when they bump into each other, click, they stick.
Right. You need more energy to pull them apart.
A higher boiling point. That makes sense.
But now, bring in the iodoethane crowd. Iodine is massive.
How massive.
Think sumo wrestlers, a whole crowd of huge, heavy sumo wrestlers.
Okay, I have that image in my head.
Now, their magnetic badges might actually be a little weaker than the chlorine ones, but does it matter?
I see where you're going. If you have a room packed with 1,000 sumo wrestlers.
They're dense. They're heavy. Their sheer mass creates so much friction and, well, stickiness. It is incredibly difficult to move that crowd.
Not because of the magnets, but just because they're so heavy.
Precisely. That is why iodoethane has a much, much higher boiling point. The sumo wrestlers win.
That is a brilliant image. Okay, let me play devil's advocate with a real example.
Go for it.
A student's listening thinking, okay, but fluorine is really polar.
It is.
So let's compare fluoroethane and iodoethane. What do the numbers say?
Great question. Fluoroethane, with its superpolar CF bond, boils at minus 37 degrees Celsius.
Minus 37, so it's a gas at room temperature.
A gas, yes. Barely holding on to itself. Now, iodoethane. Same two carbons, just with that huge iodine atom. It boils at 72 degrees Celsius.
72, that's a 100-degree difference.
It is. That's the power of those London dispersion forces. The sumo wrestler effect. It completely dominates.
Okay, I am completely sold. Weight wins. Now,
Mm-hmm.
let's go back to my refrigerator question from the very beginning.
Let's do it. This shows why the concept exists.
How does this solve that real-world problem?
Well, engineers needed a refrigerant gas that would boil at a very specific temperature, around minus 25 to minus 30 degrees.
Right, for the compressor to work.
So when they had to replace the CFCs, they couldn't just pick any random chemical. They had to find something with a matching boiling point.
So they looked at the periodic table.
And they played with the weights and halogens until they found HFC 134A. It boils at minus 26.1 degrees Celsius.
A perfect match. So they literally engineered the physical properties to fit the machine.
Exactly. It's a physics matching game.
Fascinating. Okay, so we've covered weight versus polarity. What about the other factor that always shows up in exams? Shape.
Ah, yes. Branching. Isomeric haloalkanes.
The textbook always says branching decreases the boiling point. It just feels like another rule to memorize. Why?
Let's use another analogy. Spaghetti versus ball bearings.
Okay, I'm listening.
Imagine you have a bowl of uncooked spaghetti, long, straight sticks. If you try to pull one stick out, what happens?
It drags the others with it. There's a lot of surface area, a lot of friction.
Right. That's a straight chain molecule like 1-chlorobutane. They can line up and touch each other all along their length. More touching means more van der Waals forces.
So higher boiling point, harder to pull them apart.
Now, what if you have a bucket of round ball bearings? You try to pick one up.
It just rolls away. There's very little contact between them.
Exactly. Spheres have the lowest surface area for their volume. When you branch a molecule like tert-butyl chloride, you're making it more spherical. You're tucking the carbons in.
So because it's rounder, it can't touch its neighbors as much.
Less surface area contact means weaker forces, so the boiling point drops.
Spaghetti gets tangled, high boiling point. Balls roll away, low boiling point. That is crystal clear.
You've got it.
Okay, we've hammered boiling points, but let's talk about the other two properties, solubility and density.
Very important, especially solubility. This is where the dissolves rule seems to break.
Yes, explain this to me. We just established that haloalkanes are polar. They have the magnet,
They do.
and water is extremely polar.
The most polar, yeah.
So polar should dissolve in polar. But the book says they are practically insoluble in water. Why?
The rule isn't lying, it's just incomplete. Think of water molecules as being in a very exclusive, tight-knit club.
An exclusive club.
Yes, they are obsessed with each other. They form very strong hydrogen bonds. They're all holding hands very, very tightly.
Okay, so they're a fleek.
A strong one. Now, here comes a haloalkane molecule. It has a polar head, the halogen part. That's like its ticket to get in.
Okay, so the water looks at the ticket and says, okay.
But the problem is the rest of the molecule, the alkyl group, that long carbon chain, it's hydrophobic. It's oily.
It can't form hydrogen bonds.
Right. So it's like showing up to a formal party wearing a nice tuxedo jacket, but with muddy sweatpants on.
The club won't let you in.
Exactly. To dissolve, the haloalkane has to break those strong water bonds to squeeze inside. But the energy it gives back isn't enough to pay for the cost of breaking up the water club.
The energy cost is too high. Water would rather just stick with itself.
Correct. So it stays separate. But if you put it in an organic solvent like benzene, it dissolves perfectly. The sweatpants are welcome there.
That makes so much sense. It's a battle between the polar head and the oily tail.
And water is just too picky.
Okay, last one. Density. The sink or float test.
This one is quick, but very useful in the lab.
So if you mix a haloalkane and water, which layers on top? I would guess the haloalkane, since oil slopes.
Usually you'd be right. Simple hydrocarbons are lighter than water, but halogens change the game.
Because of the weight again?
Precisely. Fluorine and chlorine are relatively light, so monochloralkanes usually float. They are less dense than water.
Okay.
But bromine and iodine are heavy, and if you have multiple chlorines, like in CCl4, that's also very heavy.
So those compounds are denser than water.
Yes. If you pour bromothane or iodoethane into water,
It will sink to the bottom. It forms the lower layer.
that's a great practical observation. If you see the organic layer at the bottom, you know you're dealing with a heavy halogen.
All right. This has been incredibly helpful. Let's try to summarize the key takeaways for the exam.
Let's do a quick recap.
So, core idea. It's a battle between molecular weight and polarity.
Mental picture. Remember the concert crowd. Heavy sumo wrestlers are hard to disperse.
And the golden rule. Weight wins. So for boiling points, iodine beats fluorine.
Shape matters. Don't forget spaghetti versus ball bearings. Branching makes a molecule rounder and lowers its boiling point.
And the water club. Haloalkanes are not soluble in water because they can't break the strong hydrogen bond network.
And finally, density. Heavy halogens sink. Bromides and iodides are denser than water.
It really is that straightforward. You don't need to memorize tables. Just ask, is it heavy? Is it round?
And the answer will reveal itself.
Perfect. Now, before we sign off, we always like to leave our listeners with a provocative thought.
Yes. So we talked about why haloalkanes don't dissolve in water, but I want you to think about why nature has this dissolves rule in the first place. Why is nature so lazy?
Lazy.
Yes. Everything is about energy. Nature always wants to be in the lowest, most stable energy state. The reason water rejects oil is not some chemical dislike. It's because breaking its own bonds costs too much energy.
Nature won't pay the energy bill unless it gets a good return on its investment.
Exactly. Chemistry is just a form of economics. Nature is balancing its energy budget. Think about that the next time you see your salad dressing separate.
The battle of the energy budget. I love it. Thank you all for joining us on this deep dive. Keep visualizing those sumo wrestlers.
Happy studying.